So for related rates, we have a process where we start with some kind of situation. Frequently that involves some geometric figure, so we're probably going to want to draw that first. And then we want to go through and look at rates. What rates are given to us and what is the rate that we are looking for? Okay, what is it asking us to find? And then we write an equation that relates these rate variables. Now the thing about this equation right here is that time is not a variable in this equation. Okay, so for example, if we're talking about like the area of some kind of figure, then maybe we have a base and a height, but time is not a variable in that equation. Or maybe we're using the Pythagorean theorem, or maybe a trig function, but time is not a variable. And then in step 4, we're going to take the implicit derivative with respect to the variable t for time. Okay, so the original equation is not going to have time in it, but then we take the derivative with respect to t. So that also means that every variable will have d something over dt attached to it. Okay, so all variables will have d of whatever over dt attached. Okay, all right. And then we are going to substitute the values that were given into that equation, or rates that were given into that equation, and we're going to solve. We might need to go back and use the equation, the original equation from step number 3 to find some unknowns. All right, so let's look at an example. For this first one, we have air being blown into a spherical balloon at the rate of 10 cubic centimeters per minute, and that is a constant rate, it is not changing. Find the rate at which the radius is changing when r is equal to 5. Okay, so first of all, our given in our, first our picture. Here's our spherical balloon. Not a great picture, but that's okay. All right, and it's got a radius, okay? And we are given that air is being blown into that at 10 cubic centimeters per minute. The fact that we're talking about cubic centimeters here tells me that that is a rate of change of volume. So the rate of change of volume, or dV over dt, is equal to 10 cubic centimeters per minute. Okay, and then it says find the rate at which the radius is changing. So this is telling me that I'm looking for the rate of change of radius. So I want to know what is dr over dt if I use r for radius. And this is going to be some amount of centimeters per minute, or some rate of change of centimeters per minute. Okay, so step 2, I've got my given rate, which in this case is just the change in volume, and the desired rate, which is dr over dt. And then for step 3, I need to write an equation that relates these variables. Well, because this is a sphere, I'm going to use the formula for volume of a sphere, which is 4/3 pi r cubed. Okay, and so that relates V and R. Notice T is not one of these. And then for step 4, we're going to take the derivative with respect to T. So take the derivative with respect to T of this entire equation. So I get the derivative of V is 1 times dV over dt. Okay, over here 4/3 pi is a coefficient. The derivative of r cubed is 3r squared, so I combine those to get 4 pi, because the 3's cancel, r squared, and then using the chain rule, because we have an r and not a t, we multiply by dr over dt, okay? And so this is my related rates equation. Step number 5 tells me to substitute in any of the known values and solve, okay? So that's where I'm going to take my 10 centimeters cubed per minute and put that in place of dV over dt. dr over dt is the unknown, but I also need to know what r is, and that's where I care about the instant. So the instant that we are concerned about here is when r is 5. This is our instant. Okay, so what that means is I can plug 5 in for r. I cannot plug 5 in for the r that was in the original volume formula, and this is important. That's why I did not label r over here. Let me add a little room here. Okay, I'm going to make a note of that we should not, so don't label with changing values. Okay, so since 5 is the radius at a specific instant, I do not want to label my R with 5 because that would mean I have a constant radius, meaning the volume is not changing. All right, so back to this. I'm plugging 5 in for R. So this equation becomes 10 equals 4 pi times 5 squared times dr over dt, and now I can solve for dr over dt. All right, so that is 5 squared is 25 times 4 is 100. Dividing both sides by 100 will give me 1 over 10 pi, so dr over dt, oh, there's my t, is equal to 1 over 10 pi, and I do need units, and that's going to be centimeters per minute. Okay? Next one, a 20-foot ladder slides down a wall. The base is moving away from the wall at 2 feet per second, so that's a given rate. How fast is the other end moving down the wall when it is 12 feet up? So, first of all, let's start with a picture. We've got a wall. We can assume that the wall is at a right angle to the floor, and we have a ladder that is leaning up against it. Okay, we're told that the ladder is 20 feet long. Now, because this is a constant length, I'm going to go ahead and label that hypotenuse with a 20. All right. If the ladder was changing lengths, then I would not put that on there. I would need to use a variable. Okay. Base is moving away from the wall at 2 feet per second. So if this is my base, let's label that with a B, or you can use whatever variable you'd like. That tells me that the rate of change of B, of the distance from the wall to the bottom of the ladder, is 2 feet per second. So that's giving me dB over dt is equal to 2 feet per second, okay? And then the question says, how fast is the other end moving down the wall? So we want to know how fast is this moving, sliding down. And I'm going to call this H for height. You can use a different letter if you want. You can use whatever letters. I would, anything but T. I would also suggest you stay away from D because dd over dt gets a little confusing. Okay, so I'm going to call that H. And dH over dt is our desired rate, and this is also going to be in feet per second. All right, so what equation, step 3 now, what equation relates these variables? And in this case, it's the Pythagorean theorem. So I'm going to write that as b squared plus h squared is equal to 20 squared. Okay, you can put 400, it doesn't matter. And now, once we have this equation, we are going to differentiate with respect to t. So take the derivative with respect to t. We get 2b times dB over dt plus 2h times dH over dt is equal to, and the derivative of this is not 2 times 20. The derivative of 20 squared, which is a constant, is just 0. Okay, so step number 4, now we are that is step number 4. We've taken the implicit derivative, and now we are plugging in our values, okay? Now, this is one where we're going to need to go back to our equation to find something. We are given that the instant is when it is 12 feet up. So the instant here is when h is equal to 12, okay? But I have another variable. I know dB over dt is equal to 2. I know that h is equal to 12. This is my unknown, but I need to know what b is. So to find that, I'm going to go back to my original situation geometrically, okay? And I'm looking at the instant when this base is b, when the height is 12, and this is 20, and so by the Pythagorean theorem, I get that b is equal to 16. That's a special right triangle. You can work it out if you need to, but b is 16, so I can put 16 in for b, 12 in for h, and 2 for dB over dt. The one other thing I'm going to do to make this equation a little bit simpler is I'm going to go ahead and divide the whole equation by 2. So I'm going to get rid of these. 0 divided by 2 is still 2. So if you have the 2's in there, not a big deal. This is just going to give me smaller numbers to work with. Okay, so b is 16, dB over dt is 2, h is 12, and dH over dt is the unknown. Okay, so solving this, let's come over here. Solving this, we have 32, and we're going to divide by 12, so dH over dt, I'm doing a couple algebra steps at once here. Subtracting 32 from both sides and then dividing by 12, which is going to give me, that can reduce by 4, negative 8 over 3. and unit here is feet per second. Okay, let's talk about this real quick. Does it make sense that I have a negative? Well, what does dH over dt represent? That represents the rate that this distance is changing as the ladder slides down the wall. So yeah, it does make sense that it's negative because we have a decreasing amount. Okay, so dH over dt is negative 8/3 feet per second. Or you can say it is sliding down at 8 feet per second. Okay, third example. Two trucks leave an intersection at right angles, traveling at 40 and 60 miles per hour. How fast is the distance between them increasing a half hour later? So again, we have a right angle situation. We have a triangle. Okay. So something like this. And we know that, okay, in this case, this distance is increasing because one truck is going this way, one truck is going this way. I'm going to call this X, Y, and Z. You're welcome to use A, B, C if you prefer. That's a right angle. Okay, so I know that my one of my trucks is traveling at 40 miles an hour, so I'll call that X. So the rate of change of the distance X, dx over dt, is equal to 40 miles per hour. And then dy over dt, that's the distance between the rate of change of the distance that this truck has traveled, and that's going to be equal to 60 miles per hour. So 60 miles per hour. And then the question says, how fast is the distance between them increasing? And that is z. So we are looking for the rate of change of z, and that is also going to be in miles per hour. Okay, so again, we're using Pythagorean theorem, and we have x squared plus y squared equals z squared. This relates our variables x, y, and z. Then we're going to take the derivative with respect to t implicitly, which will give us 2x times dx over dt plus 2y times dy over dt is equal to 2z times dz over dt. Okay, and then algebraically, I'm just going to get rid of these 2's to make that easier. So what do I know and what do I have? Well, my instant is a half hour later, okay, which is not a distance, but I can use that to figure out what the distance is. Technically, I'm using distance equals rate times time, but I think that's one we don't really need to write out, okay? So after half of an hour, if this truck here has traveled for half an hour at 40 miles per hour, x is going to be equal to 20 miles. Okay, so the instant is 20, and then y will be equal to 30 miles, all right? And then I am going to use the Pythagorean theorem to figure out that this is 10 root 13, or you can leave it as root 1300. It doesn't matter because this is the kind of question we would use a calculator for anyway at the very end, because we're talking about miles per hour, and having an irrational representation doesn't make a lot of sense for truck distance and speed. Okay, so we know that x is 20, y is 30, z is 10 root 13, and we also know dx over dt and dy over dt are 40 and 60, and we are solving for dz over dt. So that means I have all but one of my variables represented, and I can plug these in. So 20 times 40 plus 30 times 60 is equal to 10 root 13 times dz over dt, which is what we are solving for. Okay, and then we solve from here, and again you can use a calculator to get your final answer here. I'm going to go ahead and divide everything by 10. So I have 80 plus 180 is going to give me 260 over root 13 is dz over dt, which comes out to about 72 miles per hour.